In this video, I'm going to go over the carboxylic acid derivative acidity and reactivity. So for this first problem here, we have rank the following compounds in order of decreasing reactivity towards NOH. So NaOH, we know that sodium is a spectator ion with a full positive charge. That means that the OH would have to have an OH minus ion. So this OH minus ion is a hydroxide ion, and we know that this hydroxide ion is a base. And an important note to know is that acid-base reactions are going to be one of our fastest reactions in organic chemistry. They're going to be way faster than nucleophilic acyl substitution. So in this case, we see that we have a very acidic hydrogen there connected to the carboxylic acid. The OH minus is going to be very attracted to that H. So this is going to do an acid-base reaction, forming a carboxylate here, making this carboxylic acid the most reactive towards NaOH. And then we go towards the carboxylic acid derivatives, where the most reactive derivative will be the acyl halides. The second most reactive derivative would be the anhydrides. And then it'll be the esters. And then the least reactive would be the amides. So this is due to the leaving group ability and the electronegativity of the leaving group. We know halides are very electronegative, withdrawing the carbonyl carbon's electrons, making that very electrophilic and very reactive. Oxygen is less electronegative than halides are, which is why they are less reactive than the acyl halides, but the leaving group is very good because of its resonance. Whereas the OR here and the nitrogen cannot do any resonance, making them very bad leaving groups. However, esters are more reactive than amides because oxygen is more electronegative than nitrogen is, which makes oxygen be able to hold that negative charge better than nitrogen. So our second most reactive molecule here to OH minus would be the acyl chloride, and then the anhydride, and the very least reactive would be this amide here. Now let's move on to the next problem. Which of the following molecules is the most reactive compound towards NaOC2H5? So we know that this will also be a base, which is an alkoxide. So now we have to look for a most acidic hydrogen. So I'm going to redraw these compounds here into these structures that is easier to see the hydrogens and the conjugate bases. Okay. We see here that this hydrogen is going to be our most acidic hydrogen because once we deprotonate it, we will have this conjugate base, where this conjugate base is able to do the most amount of resonance compared to the other conjugate bases. The conjugate base of this molecule is not even able to do resonance because we have an sp3 roadblock there. The conjugate base of this is able to do resonance with the ring, but it is still less than the resonance of the carboxylate here, because this negative charge is able to do resonance with the carboxylic acid and also the benzene ring. Since there's more resonance, the conjugate base is more stable, making it a weaker conjugate base and therefore a stronger acid. So the most reactive towards the base would be the most acidic molecule B. Now let's move on to the next problem. Rank the following compounds in order of decreasing acidity, where 1 is going to be the strongest acid. So here we have carboxylic acids in all of our molecules. So I'm going to redraw these into its conjugate bases here, where these blue structures are the conjugate bases or the deprotonated version of the acid. So we see that we have NO2 groups on all of these rings, where NO2 is an electron withdrawn group inductively enter resonance. So if it's connected to a benzene ring, we see that the NO2 is going to create positive charges on the ortho and para positions. We see here positive charge on the ortho positions here and the para position here. So looking at the benzene rings here, we see we have a positive charge on the ortho position and the para position there. ortho position, para position there. We know that this negative charge is directly supported by this positive charge underneath, making this the most stable conjugate base, therefore the weakest conjugate base, and that makes it the strongest acid. That means that the other molecule that could do resonance, providing full formal positive charges, would be the second most acidic, because these two structures here are not benzene rings, so they cannot do any resonance. There's not going to be any full formal positive charges. So the other factor we have to consider is the inductive effect. We notice that the nitrogen, the very electronegative nitrogen here, is going to withdraw electrons from this negative charge closer, whereas this nitrogen is farther away, so it's not going to withdraw as much electrons. So that means that these electrons here, the negative charge, is more delocalized, making it more stable. And with a more stable conjugate base, it's a weaker conjugate base and therefore a stronger acid. So this would be 3 and this would be 4.